Cool. Yeah. Everybody, welcome to today's talk. So we have coming from London, my academic brothers, younger academic brothers. So we have Leo McCormack starting off, who will speak about braided Lie algebras and universal balance.
Thank you very much, Father. Thanks very for letting us come. So it's going to be about braided Lie algebras and the universal enveloping algebras, where the general motivation is kind of the usual one that Lie algebras are an interesting algebraic kind of substitute for the Lie group. And then the problem with Lie algebras is that you have known associativity, and so you go to the universal enveloping algebra to recover associativity, which means that you can use usual techniques and so on to study representation theory and so on. And the reason why we're going to study braided Lie algebras is because they were introduced by my supervisor, Sean, in order to kind of solve the so-called Lie problem of finding a Lie algebraic-like object that generates, it's finite dimensional and generates the Q deformations of the enveloping algebra, which was at that time kind of unsolved. And so, yeah, it's just quite nice. So the idea here is just to kind of revisit the axioms, add a bit more structure, study the universal enveloping algebra a bit more, and then come up with a general theory of how these braided Lie algebras arise in general, and hopefully to further settings. So the axioms of a braided Lie algebra are some other people, when they study braided Lie algebras in symmetric categories, say, then they just generalize the flip map by a categorical braiding. I should probably say what braided category is first. Sorry. Braided category is just a monoidal category, so a notion of tensor product, and a notion of associativity for the tensor product unit and so on. So the usual axioms, just like for vector spaces, but you can be up to isomorphism for the associativity. And then you add an extra structure, which is a natural isomorphism from the tensor product to its opposite tensor product. And so it's just a generalized flip map. And but the key thing is here is that we are going to consider, we want things to work in the case where the braiding is not involutive, because otherwise you're just kind of essentially dealing with vector spaces. Yes, yeah, this is a braiding, yeah. And the key theorem, but yeah, we want everything to work here because symmetric categories are a lot of things just pass through to symmetric categories from, say, vector spaces quite easily. But in this case here, it takes a bit more work. And the key theorem that is used when studying braided categories is Maclane's coherence theorem. Which simply states that basically you can do every computation using diagrams. Specifically, if you represent, all maps in the category are going to be represented by strings that are labeled. And in particular, the braiding is going to be represented in this way, where it reads down the page. So this reads as V tensor W going to W tensor V, where the tensor product is just denoted by juxtaposition. And this is the application of the braiding to this tensor product. And Maclane coherence theorem says that if we denote tensor products by juxtaposition, using the fact that all categories are equivalent to strict categories, and we denote the fundamental braiding in this way, and we kind of draw functoriality of this natural isomorphism in this way here. So if I apply a morphism just to V inside this tensor product, and then apply the braiding, then this being a natural morphism means that the composition of first the braiding and then the map on the second strand now, these two maps are equal. And then lastly, one of the axioms that you have for this is the so-called hexagon axiom, which tells us that if we apply the braiding between V tensor W with Z, then this is equal to, isomorphism, the first applying the braiding between W and Z, and then applying the braiding between V and Z. And so if we stick to these diagrammatic rules, which encompass the axioms underlying braiding, then MacLean's coherency says that if you have a braided diagram, if you have two braided diagrams that are equal to each other, then that's the same thing as saying that the composition of maps that they represent is equal to each other. So it's, yeah. And so that's why, yeah, we can basically give the axioms in this way. So the axioms for a braided Lie algebra were motivated in the same way as kind of classical theory, where you have a Lie group and then you differentiate the adjoint action and see what it looks like at the Lie algebra. And then here, using notions that in quantum differential geometry, your Lie algebra is essentially a sub-object of your Hopf algebra, in the sense that the functions of on the group, so your quantum manifold quotient down to the one forms. Then Sean studied the properties of the braided adjoint action, which is denoted here. And so this just generalizes the usual adjoint action, where there's just a flip map here. And if you study the properties of the braided adjoint action, you get this axiom here, which is basically some braided Jacobi identity. And then we're going to impose this axiom here. And if we look at it, it's kind of replicating the notion that a key property of a Lie algebra is that when you embed it in this enveloping algebra, it's co-commutative. And that has implications towards its representation theory. And so here you want a Lie algebraic object, and so you want to replicate this notion of co-commutativity. However, in a braided category, asking for a coalgebra to be co-commutative in this sense here, the most obvious sense, is far too strong. You don't have enough examples. And so you come up with this weaker notion where it's co-commutative up to the adjoint action. So it's, yeah. So it's just a weaker notion, and then we'll see why this is quite nice. And also, I should say, it's motivated by examples. So you have lots of examples of things that satisfy this. And if this braided co-commutativity holds, then you get a very natural axiom that the adjoint action is just a coalgebra map, which, I mean, this will have implications towards the representation theory, as we'll see. And then lastly, in the braided Hopf algebra, you have a unit and it interacts with the adjoint action in this way here. And so with this, you then take this as a definition for what a braided Lie algebra is. So braided Lie algebra is just defined as a coalgebra in the category equipped with this binary operator that satisfies these axioms. Now, the fact that it's a coalgebra is important because essentially we want to have, a key feature of representations of ordinary Lie algebras is that their categories of representations are monoidal. And when you're dealing with Hopf algebras and so on, then the coalgebra is what exhibits this monoidal structure, as for the usual enveloping algebra. So in order to kind of encompass that, you want your underlying structure to be a coalgebra in the category. And then you have your co-commutativity, you have that it's a morphism of coalgebras. And then you have these axioms here if it's a unital braided Lie algebra. And then you weaken it by saying that it's split if it only satisfies this. And this weakening of the axioms is again motivated by examples. So as I was saying, the key canonical example is if you take the degree 0 and the degree 1 components of the enveloping algebra. And these together form a braided Lie algebra in the category of vector spaces with its usual tensor product and trivial flip map as its braiding. And so if you impose that it's unital in this sense here, then these axioms just come out as the usual Jacobi identity for Lie algebra. So it does generalize the notion of ordinary Lie algebras. And I should say at this stage, one of the key drawbacks that we try to address is the fact that this set of axioms does not incorporate a notion of antisymmetry. So in reality, at this stage here, all you have is a left Leibniz algebra. You need to manually impose antisymmetry if you want a Lie algebra. And then another success of the set of axioms is if you look at braided Lie algebras in the category of sets, using as Cartesian products of sets as a monoidal structure and just a flip map again, then you're forced to have a diagonal coproduct. And then the Jacobi identity, the pentagonal Jacobi identity, just comes up as the usual rack axioms, well, axioms for a rack. And so, so you have these two kind of quite different theories that are actually, well, are intended to kind of simulate the same thing. So conjugacy classes as a kind of finite Lie algebra and then the usual Lie algebra. And they're all incorporated in this single theory of braided Lie algebras. And a key map associated to these is this map here, which you'll notice that if I then compose this with a product, then it about looks like the usual enveloping algebra quotient relations for the usual enveloping algebra. And then this rack operation, this rack braiding is the one that's used to generate the associated group to a rack. So this morphism here is important. And so what does it look like in general for braided Lie algebras? It looks like this, and we denote it in this way here. And the key kind of new feature here is that we found that, in fact, the axioms for a braided Lie algebra can be completely equivalently written in terms of this braiding. So the bracket is incorporated in the braiding in this way here, and then you can recover the bracket from the braiding in this way here. And if you write down the axioms, then all you get is that it is a braiding, hence the name. So it satisfies the usual braid relations. Then the co-commutativity axioms come out in this form here. The fact that it's a map of coalgebras comes out in this form here. And then you have this additional axiom here. And then these two can be nicely packaged up equivalently in this way here, which just says that the braiding is a map of coalgebras. So in fact, all a braided Lie algebra is a coalgebra equipped with a braiding of coalgebras. That crucially satisfies this additional axiom, which is what allows you to go from a braiding back to a bracket. But if you drop this, then this was the notion of a generalized braided Lie algebra. But yeah. And the unital axioms come out into this. And we say that the braided Lie algebra is regular if this morphism, this braiding is invertible. And because you have this correspondence between brackets and these braidings, which we'll call fundamental braidings, then as expected, properties of the bracket get reflected into properties of the braiding. So just as a trivial example, if the bracket is trivial in this sense here, then in fact the braiding is involutive. So one of the interesting previous results of Sean is that he studied, I mean, you get basically new solutions of the Yang-Baxter equation from you start off with a categorical braiding, so a solution of the Yang-Baxter equation, and using braided Lie algebras, you generate new ones. And they cannot be trivial. And well, they cannot be symmetric because otherwise your braided Lie algebra is trivial. Yes?
Let's see why this is a braid. So in the next, the example you gave for.
Oh, sorry. Yes.
Yeah. So you have a flip, plus, bracket, and C, pencil C.
Yes. And then, I mean, yeah, if you just go, yeah. So the here, oops, sorry. This part here for the rack operation, this is well known. This was defined in order to find the associated group of a rack. And then here, basically, this was a kind of novel feature, well, a novel observation of ordinary Lie algebras.
But then X bracket Y and so T should be some probably something I don't see.
So, I mean, if you can go through the axioms, should I go through?
Yeah.
Yep. So, I mean, we can. Okay, I mean, what I could say as well is that this pentagonal Jacobi identity does imply that it's a that it's a braiding, and then I could check it's a consequence of the Jacobi identity. Is that sorry?
maybe also a quick question. So this L being regular, so go to the next slide. So yeah, is this that you say that psi -1 exists? So can you say what this means in terms of the bracket?
So in terms of the bracket, it's well, we use it later in order to define notions of antisymmetry. That's one of the applications of this. But I mean, if we look at the fundamental braiding associated to an ordinary Lie algebra, then it's just a feature of the braided Lie algebra as such. So it doesn't really reflect anything about the bracket as such. So if I do this, then it'll be minus sorry. What will it be? So sorry, so if I flip this around, so C tensor. So this way here.
So it's not here to point out what is the property that you are breaking the bracket is satisfied in order to have a regular.
No, not really, no. But it's a feature that basically all braided Lie algebras have, and it is useful for defining further structure on a braided Lie algebra. But in terms of whether you can see that from the bracket itself is not entirely clear. I should say later on when I discuss the notion of an IP braided Lie algebra. Well, actually, that's going to be the next slide. Okay, so they'll kind of be answered, I guess, here. So the one thing that was missing from the axioms of braided Lie algebra was that, yeah, we've differentiated the notion of done the analog of differentiating the adjoint action, but a key feature of ordinary Lie algebras is that also if you differentiate the inversion map at the level of groups, then you get that x goes to minus x at the level of Lie algebra. So you get a remnant of the inversion. And so we've kind of manually added it in as an axiom for braided Lie algebras as by following the same structure. So if you have a braided Hopf algebra that is a braided Lie algebra, then what does this antipode satisfy? And so it satisfies this just immediately from the fact that the adjoint action is an action and the antipode axioms. And then if it's braided co-commutative in this sense, then the antipode is a module map. And then you've got your usual anti-co-multiplicativity axiom, and in this case here, if it's unital. And we do the same thing where we replace the adjoint action just with a bracket. And it's called this an IP braided Lie algebra. And maybe if I jump ahead, yeah, that's kind of if the antipode, if this notion of inversion is invertible, then your braided Lie algebra is necessarily invertible. And so, just as an example, if you consider your classical case, then all IP maps, so this generalized notion of inversion, has to have this form here on the Leibniz algebra, actually, and then here on the degree 0 part, where this is just some map that lies in the center, and that is 0 on the derived subalgebra. And I've highlighted in the dotted bracket that this is the classical one that you have for usual ordinary Lie algebra. So here in the braided setting, you just get, if zeta is 0, basically you recover the expected inversion map at the level of ordinary Lie algebras. And then at the racks, then is having, yeah, it's just saying that it's that the rack operation is invertible. And so from these examples, you can see that the IP map need not be unique. However, the way it acts is uniquely defined. And so that will be an important property for later. So even though you have different IP maps, in fact, when they act on the Lie algebra itself, then there's no distinction. Yeah, and then interestingly, you can get these ones beyond the classical case for, say, the Heisenberg algebra. It admits IP maps are not just minus X. And so again, here the top, all the axioms for the IP map are written in terms of the bracket. By using this correspondence between the bracket and the fundamental braiding, then we can write it in this way here. If the braided Lie algebra is regular, and then as I said, if the inversion map is invertible, then your braided Lie algebra is regular. And then this will be a useful feature of later, a useful observation, that just as the antipode of a Hopf algebra can be viewed as a map from a Hopf algebra to its opposite, then you have an analogous notion at the level of braided Lie algebra. So just from this property that it satisfies, then there's a natural candidate for what opposite braided Lie algebra should look like. And then these turn out to indeed be braided Lie algebras. So the fundamental of braided Lie algebra. And then lastly, the one thing that was also missing was a notion of an antisymmetric braided Lie algebra. So there wasn't a notion. And then the way we've defined it is just by kind of copying the usual setup of how you define a Lie algebra from a Leibniz algebra. So in the classical setting, there's the category of left Leibniz algebras is equivalent to that of the right Leibniz algebras by just defining a right bracket as the flip of the left bracket. And then if you apply your inversion map, then you get, so in the algebra case, you can go from a left Leibniz algebra to a right Leibniz algebra. And then this will again be a bracket of right Leibniz algebra. And then in the Lie algebra case, you just ask for these two to be equal. So we kind of just followed the same procedure. We went from left algebras to right algebras, took the opposite, which is essentially what this does, and defined a notion of antisymmetric braided Lie algebra. And so it comes out as L just being antisymmetric if this bracket is equal to, so if the bracket of the algebra, you apply the inverse, then this turns out to be the bracket of a right braided Lie algebra. So if these two brackets are equal, then we call the braided Lie algebra antisymmetric. And the crucial feature of this that kind of pops out, which when it generalizes this, is that in fact this left braided Lie algebra and this right braided Lie algebras are braided Lie algebras on the same coalgebra. So we kind of imposed, which is why we imposed the opposite. But it comes out, so it's quite natural is what I'm trying to say in a really bad way. And again, antisymmetry is then reflected in the property of the fundamental braiding. So if it's cubic on the entirety of L tensor L, then it is antisymmetric. However, the problem is that braided Lie algebras, as we saw from examples, are kind of viewed as homogenizations of ordinary Lie algebras. You always have this extra degree 0 part floating around in order to define a braided Lie algebra. So it's too strong to ask for it to be antisymmetric on the whole thing, because you have this extra thing. So the only thing that we did was we saw that if your essentially your minimal polynomial of your fundamental braiding is cubic in this shape here, then you can say that your braided Lie algebra is antisymmetric. And later on, I'll just note that an example is all Q-Hecke matrix braided Lie algebras are necessarily antisymmetric. So the SL2, well, the Q deformations of SL2 are antisymmetric in this generalized sense. And then, as I said, this right bracket is just the usual one that you expect. Then we also defined the notion of a Lie-like braided bialgebra and Hopf algebra, again, motivated by just you want to generalize the axioms of an enveloping algebra. So a feature of the enveloping algebra is that it's a bialgebra and it has a compatible Lie bracket on it, but that's not just the standard one you can have because it's induced by the Lie algebra itself. And so again, we follow the same procedure. We consider a braided Hopf algebra, see what happens for the compatibility between the adjoint action and the new structure, which is here the product. And we just get that the adjoint action is a modular algebra. And so we take those as axioms where we just replace with a bracket. And these, yeah, this was meant to arrive slowly. Yeah. And so, and then these axioms here can be written in terms of the fundamental braiding in this way. The reason why we keep on going to the fundamental braiding is firstly, it's much easier for computations. And also it kind of looks nicer because it's just saying that the map of algebras is kind of compatible with the braiding in this way here. So it's. So that's a definition.
Oh, sorry.
Yeah, sorry. And so, yeah. And so psi tilde commutative bialgebras are defined as one where the product is equal to this new product. So that's the fundamental braiding of the braided Lie algebra. So now the structure, yeah. So now the structure is that we have not only a braided bialgebra or Hopf algebra, but one that additionally has a Lie algebra structure that's compatible with this product up.
That's the Lie graph.
Yeah. For here.
Yeah. Then brackets, then.
So there's no, apart from the one in the flip, there's no bracket here. So here this is, okay, I should, yes. So this is a product. So the bullet indicates the product. So yeah, sorry. So yeah, so in the diagrammatic notation that we're going to follow, we're going to denote the bullet as the product of B and bracket as the bracket of B. Yeah. So I mean, this is one of the kind of novel features of this definition is that in the strictly braided categories, you have a braided bialgebra, which satisfies your usual axioms that you say your coalgebra map is a map of algebras. But one thing that happens in the strictly braided case is this product here is taking this product with this coalgebra is no longer a braided bialgebra in the same category because of the strictly braided. For ordinary Hopf algebras, you don't see this because the vector spaces are trivially braided. But in non-trivial categories, then this product is only compatible. Well, this product is not compatible with this original coproduct, but this product is. So you have a braided bialgebra which has two products in this case, which are both compatible with the same coalgebra in the same category.
So you're taking category, an object from the category, and you're attaching to this object the braiding.
Yes.
But this is not braiding for the category.
No, it's a new braiding. Yeah.
So is the braiding for the category generated by that?
No.
Either.
So it's an object that lives in a braided category. So the braided category is fixed. So this new braiding is generated by the object, but the old braiding is unrelated to the new braiding.
So if the category generated by that object, so that's a product of the object, this is not braiding for this.
So yeah, it will be. It will be. You can generate a new braided category if you want by just taking tensor products and extend it. I mean, this is basically, well, I mean, you can see here, we've kind of extended the braiding on a tensor product of B tensor B is in the natural way. And so, yeah, but yeah, you can generate a new braided category. And so the point of this diagram is just to say that you get a bunch of adjunctions. So you can go from a braided Lie algebra, a braided Lie-like bialgebra, to a braided Lie-like Hopf algebra using a generalization of the braided Hopf envelope. And we've decomposed it in these two ways because now we're interested in an IP axiom. So something slightly weaker than having an antipode, but something that's, an antipode is inversion for the product map, essentially. Here, IP just means we just have inversion for the bracket. Hopf algebra means that we have inversion for the bracket and for the product. And so it just goes through these two steps, essentially. And so how this first step arises is by in the kind of standard way where you take a braided Lie algebra and you take an infinite number of copies of it, where each copy is the same underlying object, but the bialgebra structure is B, and then you just keep taking opposites as you go along. The reason for that is because then your plus one shift map, so going from B0 to B1, then becomes a map. Becomes, the map. You can basically, we saw before that the IP map can be viewed as a map from a Lie algebra to its opposite. And so if we keep taking opposites in the reverse direction, then if we take IPB, so this is just a bunch of coproducts of a bialgebra, essentially, the number of copies of the bialgebra, and we take the opposite plus, then in fact, the 0th entry here is equal as a bialgebra to the first entry here, because the two opposites are in opposite. There's a lot of opposites here. There's two notions of opposite, they cancel out. And so the identity map is a bialgebra map. And this is the first part of the construction of the usual Hopf envelope.
The difference of the Hopf class.
Yes. So
By the way,
thank you. Which one?
that graph there, that with
This one?
yeah, that's one.
Oh yeah, that does work a lot better. Thank you. So yeah, so maybe I should have said this as well. So for ordinary in categories of vector spaces, you have a notion of opposite where you just take the flip before you use a product or a bracket and so on. But there's only a single notion of opposite because your flip map is symmetric. Whereas in a braided category, then you have two notions. You can either define a new bracket like this, or you can define a new bracket like that. And so this is just it just distinguishes the two. But the key point I was trying to make, and I don't think I made it very well, is that when you define the Hopf envelope of an ordinary Hopf algebra, of an ordinary bialgebra, you take these copies and you just say that bi plus 1 is equal to bi up, and you don't need to care about which notion is it because it's just a single one. Here, the only subtlety is that you need to watch out which one you take to ensure that they cancel each other out. And so this is now an IP Lie-like bialgebra. So it's a bialgebra with a bracket and a notion of inversion for only its bracket. And then if we quotient by the antipode axioms, which is a valid quotient, then you end up with a Lie-like Hopf algebra, which is a braided Hopf algebra with a bracket and an antipode, which gives you both inversion for its product and for its bracket. So it's kind of like a braided group as such, where, yeah.
Yes, it's the H block.
Yeah, it's this functor here.
But IP and H are both like generalizations of the universal envelope.
No, not yet.
No,
So it's just a canonical way. Well, it's a universal way of passing from a braided Lie-like bialgebra to a braided Lie-like Hopf algebra.
and so dimension is small.
So here it's infinite dimensional, just the IP case. And then when you quotient down, I think you can show that if B is finite dimensional, then this is indeed a quotient. From here all the way down to here is indeed a quotient. But I think if B is infinite dimensional, then it's not necessarily. It can be a quotient or it can be an inclusion. And I mean, the canonical example, which is one example we have, and this is for the, so if I take the usual FRT by algebra and I take its ordinary Hopf envelope, then you end up with, okay, I've just written a bunch of letters here, but for CQ M2, or MN, even more generally, then the Hopf envelope of that is just the localization of CQM2 at the determinant, which is just N GLN. So that's what you recover for the Hopf envelope, for the ordinary Hopf envelope. And it turns out that if we apply it for braided Hopf algebras arising from transmutation, so if we transmute this, then we recover with this construction, we recover that this Hopf envelope, well, actually, technically speaking here, this Hopf envelope here recovers just a transmutation of that. Okay, so we've got this half covered. And then just in the usual way, when you have algebras, you can just quotient and get a commutative algebra. And it turns out that this is a non-trivial fact I should emphasize. It really is thanks to the axioms of a braided Lie algebra. So this is not true for braided bialgebras in general, but it is true for braided Lie-like bialgebras because of the compatibility between the bracket and the product. And then you can go from a commutative Lie-like bialgebra to an IP Lie-like bialgebra to a commutative Lie-like Hopf algebra just by basically going around in these ways here. But yeah, the idea was that what I was trying to emphasize is that you've got a standard construction of how to go from an ordinary bialgebra to a Hopf algebra, an ordinary Hopf algebra called the Hopf envelope in school, from bialgebra to a Hopf algebra in a universal way. It generalizes nicely in the braided setting if you take care of what you mean by opposites, and is compatible with the bracket structure. And then you can do the same thing for commutative, really like bialgebras, where here the novel feature is that you can define such a notion of commutative because of the Lie-like structure of the Lie algebra structure. And then there's one last observation is that in fact B is a commutative, side-tilde commutative braided Hopf algebra if and only if its bracket is the adjoint action. So actually the axioms are so strong if it's a Lie-like Hopf algebra that you're forced to have the braided adjoint action as your bracket. There's no other possible bracket. And this is well, yeah. And then it's regular if and only if S is invertible. So before we have that invertibility of S implies that the braided Lie algebra, the underlying braided Lie algebra is regular. But here now we have the converse as well.
How would this diagram look like for classical algebra? Because you're saying it's not the universal envelope in algebra, but it would be some finite algebra structure.
So then the next part is this, which again looks terrible. But this is basically the idea, is that now we kind of complete the picture where we now go from a braided Lie algebra to a braided Lie-like bialgebra. And here classically, this would just be going from a Lie algebra to the tensor algebra to then quotienting further to the universal enveloping algebra. Here in the, sorry, yes. So the it lives here. You just take the free multiplication and and then so this is the co-product of co-algebra. So in any monoidal category, you can take the free algebra. So here you have the category of coalgebras, braided coalgebras, which is monoidal. So you take the free algebra in there. And one tricky feature is that the category of Lie algebras turns out not to have colimits, tends not to have colimits, which is for ordinary Lie algebras, you do have colimits. But for braided Lie algebras, you tend not to have colimits in the strictly braided case. But it turns out it doesn't really matter because anyway, you're just taking the co-bracket, you're taking the co-product in the category of coalgebras, and then you have to manually show that the bracket extends nicely to this tensor algebra. So it's not something that comes for free, you just have to kind of show it manually. And then you quotient and you get this. And just as a reminder, we had, well, actually, I've got it on the slides at some point. So maybe if I skip ahead to the example, then for the braided Lie algebra, which remember, braided Lie algebras, you need to include the degree 0 part in order to have a co-product. That's the reason why you need to include it. Then your braided enveloping algebra recovers the usual and universal enveloping algebra, but homogenized. So you just add a unit that basically keeps track of the filtration and so on. So it's a well-known structure. And yeah, and then I'll talk about the other two. Oh. Could I ask how much time I have?
I don't know what 5 minutes late is.
10 minutes? Okay, thank you. So yeah, so you can go from a braided Lie algebra to a free tensor product bialgebra, which also has a compatible Lie bracket. You can now quotient to get a universal commutative Lie-like bialgebra. And why do you care about the fact that it's a junction? Is just because previously when people studied these enveloping algebras in the braided setting, they didn't have universal properties for these. They just kind of constructed it by copying the classical setting as such. But here is just to show that there are universal properties associated to these, which, I mean, I haven't used them for anything apart from stating it. Well, actually, it's useful for showing things actually in proofs. And then now the problem with this braided version of the enveloping algebra is that it's quadratic in the relations, which the ordinary universal enveloping algebra is not, right? You have xy minus yx is equal to a degree 1 component, but here it's quadratic. And the problem with that is that you no longer have an antipode. And so the thing that we included now is that you can use these free Hopf algebra constructions to adjoin essentially an antipode to your universal enveloping algebra. And if your braided Lie algebra already had a notion of inversion, then in fact you can quotient down to enveloping algebra where the inversion is inherited by that of L. So here the inversion map for here is just by taking infinite number of copies using plus shift 1 map and quotienting by the antipode axioms. But here, this one here is inherited by that of L if L has one. So it's just two Hopf algebras and they fit in this kind of picture. So U of L quotients down to US of L. This map here can be injective, it can be, well, it depends. And then this map here is a quotient. This I might skip. And just as a side comment, these two braided Hopf algebras are actually related, which makes proofs easier, but that's all I'll say. Yes? No, so we kind of have, no, there's no PPW theorem. I mean, I know that Ryan, say, had worked on the PPW theorem of the reduced versions of UQSL2 and so on, which would be a quotient of these things. But no, there's no PPW theorem, but there's kind of, so this is just to say that we define things, but just like the ordinary enveloping algebra case, normally you don't ask for commutativity across, or you don't ask for a relation across the whole bialgebra or algebra. You just define it on the generators and then it carries forward. But here it's just to say that the same thing happens. So we define it on the whole thing, but actually you can just define it on the generators, the relations. But here's the remnant, the PBW theorem, is that the PBW theorem is equivalent. Maybe you have to choose the characteristic or so on of the field, but is equivalent to just saying that the representations of your ordinary algebra are equivalent to that of your universal enveloping algebra. And this is the remnant of the kind of PBW theorem that we have, is that the category of, okay, maybe I should go through this. So we have our universal enveloping algebras defined at the top. Modules of a braided Lie algebra are defined in the usual way for any algebraic structure. You just take the axioms of the algebraic structure and you polarize them. So you just replace products and so on by actions. So here we've done the same thing. And one key feature that I mentioned at the start, the kind of success of the axioms of a braided Lie algebra, is that the category of modules of a braided Lie algebra is monoidal. And you recover a braided subcategory. Because, I mean, you kind of expect it, because a universal enveloping algebra is co-commutative as a Hopf algebra. And so its category representations is going to be symmetric. And so here we just have to restrict to the category of modules in which the bracket behaves as if it's co-commutative, essentially. So it's just a weaker version. And the only new thing we did was polarize the axioms for the IP structure. And here, this allows us to say that you can recover rigid subcategories. So indeed, it's kind of this notion of IP map generalizing inversion of the bracket is the good notion because it gives us rigid structure on the monoidal category of modules, in the subcategory, which is what you would expect from having an antipode or an inversion property. You would expect that to give rigidity. And then the statement is that the category of modules of your braided Lie algebra is equivalent to this associative Lie-like bialgebra, which is kind of the classical case. And then you have these two extensions for the two new enveloping algebras. So the category of modules where the IP structure is compatible with your action is equivalent to the modules of the ordinary algebra modules of this Lie-like bialgebra, and but only if these maps are injective, which is and then the statement that at the start that we had, that the IP map is not necessarily unique. However, the way it acts is unique. Then extends to say that actually, if it exists, your IP map, if there is a braided Lie algebra, maybe I should just read the statement. If S is equal to S prime, if L includes in this universal enveloping Hopf algebra, where it depends on what S is. So if you have these two that include into these two different universal enveloping Hopf algebras for the same braided Lie algebra, then in fact the IP structure must be the same. So you only have a unique one that gives an inclusion if it exists. And so in the classical case, we recover the homogenization of the universal enveloping algebra. Then this UH, which is one where you freely add an antipode, essentially, is just a localization of the homogenization, which if you rescale your generators, takes a simpler form. And then US of L is just this thing here, if zeta is 0, which just means that the IP map sends X to minus X, then G indeed injects into U of G. So you recover basically these extensions of U of G, and if you want, you can just quotient out the extra part. And then in the category of sets, then you recover this monoid, but importantly here, you recover what's known as the associated group to a rack. So it's just recovering well-known things. And then here we recover some group. which Sean studied previously. So this is just a more general setting behind this. Yeah. So, well, maybe this is worth saying. So an example of a braided Lie algebra and its enveloping algebra is that of braided matrices. So the generating braided Lie algebra for UQSL2, say, or SLN. And one kind of feature that arises from the literature that people were interested in is that not only can it be viewed as a kind of, well, CQSLN can be viewed as a braided group in the sense that it acts on quantum spaces, but also it coacts on quantum spaces. So it can be viewed as kind of braided group coordinate algebras. And here we just generalize this in full. And the reason you have this kind of dual property for braided Lie algebras is because the canonical example of braided Lie algebra is that arising from reconstruction theory. So, okay, yeah. So the statement I'll just give is that using Schanberg's description of reconstruction theory, where the only thing that he notices is that the association of a coalgebra of a category to a coalgebra that universally coacts on the image, but on the category essentially, is in fact you can force it to be a braided functor. And if you ask for that, then you get this notion of central coalgebras popping up. But in fact, these are nothing more than just braided Lie algebras. So there's just a canonical way of generating these braided Lie algebras. And then maybe I'll just close on the example. So this is the diagrammatic. We now have a diagrammatic definition of these matrix braided Lie algebras. So this is just the braided Lie algebra structure on matrices braided Lie algebras. And if you take the R matrix associated to SLNQ, then you recover the usual for L equals some notion of Q deformation of SLN and a homogenization, because we need to add this. We have, when we're doing braided Lie algebras, we kind of add this artificial unit in order to get a coalgebra. Then for U of L, we recover the transmutation of A of R, so just CQ M. And for U, H of L, sorry, as said before, we recover CQ GLN. So in fact, this IP property, freely generating this IP property is just equivalent to inverting the determinant. And then U S of L recovers CQ SLN, this quotient. And and then we showed that if you have a braided Lie algebra that arises from reconstruction theory, then its enveloping algebras arise from reconstruction theory here, which in this statement here is just saying that they're transmutations. And the only thing I will say is that, if your categorical braiding is Hecke, then this matrix braided Lie algebra is antisymmetric. And if the Nichols algebra is finite dimensional, then it has a notion, an inversion for the bracket. There's a notion of inversion for the bracket. And so lastly, so we extended kind of some properties of braided Lie algebras, understood how these kind of arise in the braided Lie algebra setting in a slightly more general way. The key new thing is that, which I haven't talked about, is that all of this takes place in the category of, say, CQSLN modules. And now we can choose different categories. So we can choose Z-graded vector spaces category and so on. So you get these new braided Lie algebras that generate braided versions of these Hopf algebras in different braided categories. And is there a geometrical application of this observation that Lie algebras and their enveloping algebras are just homogenizations of the usual ones? And then one thing that was mentioned in Brussels is that there's a notion of how to associate a braided Lie algebra to a bicovariant calculus on the co-quasi-triangular Hopf algebra. And I thought I had a generalization to left covariant calculi, but it turns out I'd made a Q factor mistake. So it is not. So that's still under procedure. Yes.
Questions? Comments?
My question is, so did you think about adding a Lie bracket and defining the notion of this braided Lie algebra and eventually how to quantize this, since we have also the braided bialgebra?
I mean, so firstly, I mean, I should say I've heard of the notion of a braided Lie algebra, but I mean, yeah, so okay, there's a notion of a braided Lie algebra that we just covered. You can flip all the diagrams and you get a notion of braided Lie coalgebras. What we have done as well is define the notion of a tensor product of braided Lie algebras. So there's no monodal structure on the category of braided Lie algebras, but under certain axioms, you can come up with the notion of tensor product. So I don't know if you put a braided Lie co-bracket on that, whether that does anything. I don't know. But yeah, so yeah, that would be interesting to see. But essentially, I'm not quite sure what the compatibility between the co-bracket and the bracket should be. If it's similar to that of a coalgebra and an algebra, I don't know, because I haven't looked at the definition. Sorry.
More questions? Yeah.
So, what can be said about the primitive elements of the universal enveloping algebra? Do you obtain a braided Lie algebra?
So that's what I should have also said, is that, we saw that to go from an ordinary Lie algebra to a braided Lie algebra, we have to add a unit. So you make the coproduct primitive. And you can do that in full generality. So people, if you look at a lot of, I don't know that much about other definitions, but a lot of the people that study a notion of braided Lie algebra, all they do is that they have, they take their axioms for, so here's derivation property, the Leibniz property and so on, and they just replace by a flip map. So they have a notion of this, and then is equal to, and then they have like flip maps and so on, like something like that, and so on. And then there you can take the enveloping algebra, and yes, you recover the fact that if you take the primitive part of a braided bialgebra, then you recover braided Lie algebra in this setting here. However, this setting is more general because you fix the coalgebra. So here, the coalgebra is kind of God-given in the sense that you add a unit and you ask it to be primitive. So it's the theory for going from, well, the theory of primitive stuff is included in here, but here we allow for much more general, well, we allow for any coalgebra as long as there's a compatibility condition. Does that? So it's more, so the usual theory of the generalization of braided Lie algebras is included in this way. But here, because we can change the coalgebra structure, then there is no notion of taking a primitive part, because essentially taking the primitive part is saying that you've already got your coalgebra structure, which is primitive. But here, it would be more like taking the degree 1 part. Yeah. So there's no canonical way to go from a braided Hopf algebra to the braided Lie algebra in this setting here, because we allow for a more general coalgebra structure.
Questions?
Very some your last example you change there's something as a universal network. Why don't you get U cubes? this because of the braided lie algebra I took, or
So here, yeah, so we have L as being some homogenized version of the SL2 bracket, and the reason I say homogenization is because you see there's an additional element here, and then I should say up to, so lambda, oh, here, as Q goes to 1, lambda goes to 0. So all these are correction terms, or quantum terms, whatever you want to call them. So here it's primitive, the first degree, so you get the usual SL2 stuff, and then the bracket is the same in the limit Q tends to 1. And yes, you're right that if you take the universal enveloping algebra in our theory, we get CQ SL2. But then using the fact that you can apply your quantum killing form, then you can basically have an isomorphism to UQSL2. So you have, so this is a co-quasi-triangular Hopf algebra. And then you can apply your quantum killing form, which is R2 on R, and land on UQSL2. And this is more or less an isomorphism. And so you can push forward this braided Lie algebra to a braided Lie algebra in here. And essentially, I mean, here, this structure here, you know, it was the set of the basis elements were chosen such that they replicated the SL2 case. But in reality, when you start off with the matrix braided Lie algebra, your generators are just matrix elements. And in fact, these are just a different, this choice of basis is motivated by the fact that if you push to here, look at the image and then kind of pull back, you get a smart choice of basis such that reveals the SL2 structure. But yeah, you can push everything to UQSL2. UQSL2.
so there's more how you represent I don't know how to phrase it. So what you take as a representation of your universal enveloping algebra. It's not.
Yeah.
It's not that you don't get UQSL2, for instance. This looks different.
Yeah, so it's just using a feature that this is quasi-triangular and it's isomorphic, so it's dual. In a vague sense. I mean, these are dually paired as Hopf algebras, and you can have an isomorphism of Hopf algebras in this way. But it's just when you do the reconstruction theory, because we're doing co-module reconstruction theory, you use co-quasi-triangular Hopf algebras. So you start off here, and then you go to there. Does that?
Behind schedule, but I just asked one short question. It's the same question I asked Sean a few weeks ago or last week in Brussels. What about semi-simplicity for your braided Lie algebra and root systems? And
yeah, so that would obviously be a nice next step, because there is no theory of this stuff. Yeah, so I mean, obviously at this level there's analogs and so on, but in the general braided setting, no, yeah. So that would be the nice next step. Yeah.
Okay, so if there were no final questions, I think maybe we'll move on. Thank Leo again.